Hello, my name is Chris Aden, and I'm the Senior Director of AI Solutions at LMI Technologies. And today I'm going to talk about advances in defect detection for factory applications. What's new and where things are going, and I'm going to show you by example how we're finding defects in our customers' parts. So here's an outline of this presentation. We'll look at the trends that are driving innovation in defect detection, introduce some of the key model architectures and the different modeling paradigms or platforms that we can use and customers can use for defect detection. We'll talk about model availability in terms of what's there today that we can use without a lot of customization, or in some cases with infinite customization through things like open source and other open model architectures. We'll talk about edge platforms, and in particular, the LMI inspection gadget, as well as some of the innovations on the platform, the hardware platform side, to enable optimized inference on the factory floor. And then what I'll do is wrap up with an example of an application that we solved using really both of the contemporary approaches for defect detection in factories. So just by way of introduction, what's interesting about deep learning and AI for modeling is that the rate of innovation is amazing. And as you can see from the charts, more and more people are investing and publishing new innovative modeling techniques across industry, across application, to the tune of, in this case, about 35,000 new publications or innovations a year. And so that's, I think, unprecedented. And I guess the first question that it makes sense to ask is why, what's going on? And the simple fact of the matter is some of the applications driving the trends are not factory automation applications. In fact, they're things like AI or machine learning for self-driving cars. I should say for image-based AI. Certainly there are other applications like natural language processing and such. But we're talking strictly about images. So inside of images, you've got applications like self-driving cars. Medical imagery is one of the key applications driving innovation. And even applications for social networking type use cases. That's where the bulk of the focus and, in fact, the investment is going. And so what we do at LMI is we look for the technologies that we can apply to a factory setting and a factory application, and we then take those technologies and reapply them so that we're not necessarily inventing new models, new model technologies. Rather, we're looking for ways to adapt those for our customers' needs. And so this is just a brief timeline showing some of the key technologies that we use when we're working with customers to solve their AI-based defect detection applications. And so from left to right, and what I've done is I've color-coded the two fundamental techniques for doing defect detection, and I'll talk more about those later. But it's object detection and anomaly detection, and I've color-coded those in black and blue. So object detection is in black, and you see that things like bounding boxes and even semantic segmentation through faster RCNN and mask RCNN, respectively, really started to came on the scene, if you will, back in 2017, so about 4 years ago. And then we saw growth in the application of those technologies. In fact, some of the major platforms like TensorFlow and PyTorch created APIs so that the technology could be easily accessible to other users, which was a huge contribution to the field. And then more recently, CenterNet and EfficientDet are new innovations that have improved the performance and the speed of these object detectors and semantic segmentation tools. Now, What's a little more, let's say, recent is anomaly detection. And the difference here is, and we'll go into this, but being able to detect differences from what the models were trained on. We've also seen a ton of innovation. I've just referenced the two of the, I would say, the categories of anomaly detection that seem to be getting the most attention and that we're using, in fact, to solve, again, our customers' application. And so those are reconstruction-based methods. And basically what those are doing is we're training models to be able to reconstruct only good parts. And then the thinking here is that if the model's never seen defective type features, it will not be able to reconstruct those. And we could come up with a way to measure the distance, if you will, between the reconstruction and the actual image, and then use that to identify areas where there were, in fact, defects. More recently, there's a trend in using what's called embedding similarity-based methods. And what that means is really what we're looking at is the feature map themselves, deep, shallow or deep into the network. And in this case, we might be using something as simple as a pre-trained network for a classifier, for example, something trained to do well on ImageNet. And then we would train, quote unquote, train a shallow model to see what does that feature map look like when we see good parts, and then use that same model and look at the feature map, the same vectors, if you will, the feature map, when the runtime image actually has defects. So now instead of comparing pixel to pixel, we're actually going to be comparing the features in the feature map. And again, assuming that the features are going to be very different for a normal part versus a defective part. So for what we do, these are the methods and the innovations that we've been tracking. Certainly, if you double click into any of these, you'll see some other contributions. And I think one of the key points here is it's a moving target. These technologies keep changing and evolving. So I've already alluded to it, but there are a couple of different approaches. There is object detection and anomaly detection. And so let's look at object detection first. And there's really two criteria. You either have to have a whole bunch of images with known defects, or you have just perhaps a few images, but a bunch of defects, again, known defects on the few images. So what we're showing here is two different applications. One is obviously in food processing, where we have a whole bunch of images. Each image has a couple of defects, if any, in there, and we're able to get the data we need to train a model because we can quickly gather a lot of images with few defects. In this case, the defects would be food production issues like long tails in this case the sausage, or joined sausages or misformed sausages. And so that's how we get the multiplier there is just the large number of images. On the right side, you see a life sciences application where we're showing just 3 images. And our training data set was certainly more than 3, but it wasn't the hundreds that we were able to get on the sausage application. But what you see is there's a bunch of known defects on each image. And so again, the multiplier here is not the number of images, but the number of instances of the defect or the feature per image. And so in either case, the keys here for object detection is you know what you're looking for, and you have a whole bunch of those examples. And so the other approach, which we've talked about, is anomaly detection. And again, the concept here, the method here is to train a model using only known good parts. And so whether it's a reconstruction based or an embedding similarity based, in either case, the ground truth only knows good parts, good features. And then when the model is used with parts that have defects or damage, the model won't be able to represent those things well, or at least as well as it did with the defect-free images. And you can do the comparison and determine what happened. So the takeaway here is for using anomaly detection, you may not know what the defect is, and you have access to a whole bunch of samples that are quote unquote good data. And then again, there are various ways to extract a model if you have that information. So we've talked about types of models you might use. What's very important, I think what's emerged over the past 5 years, and again, what's unique to machine learning or deep learning, is the availability of open platforms for actually performing the work that you need to take images and pre-process those images and do the training and then generate formats that are deployable. And there's two primary platforms that are used for this, TensorFlow and PyTorch. I'd say they're competing platforms. At LMI, we maintain expertise on both platforms. Sometimes we find models that have either partially been implemented or the implementation is more straightforward in one or the other. But again, the new aspect of being able to develop these technologies is that the platforms are available and they're actually production worthy. These aren't just sandboxes that can be used to prototype something, and that's very important, especially for our customers when our models need to be deployed in a production, high volume factory environment. And so looking a little closer at what that means in terms of the models that we introduced. First, if we look at the object detectors, what I'm showing on the right is just a snapshot from the object detection model zoo. And what we're showing is how easy, once you're familiar with the type of model that you're trying to extract, it is to get a good starting point. And in this case, what you see is a lot of the different models that have been pre-trained for certain applications, as well as what types of relative speeds and performance you can expect, and even what the outputs are going to be. And so given that you have a platform, you have these APIs, you have models to start with, that just means that you've got a lot of work that's already been done that you can use when you start to approach your problem or your customer's problems for object detection, when you're looking for, again, these known defects. And on the anomaly detection side, I would say that it's our experience that these anomaly detection models have not been streamlined to the extent that object detection has. But you're fortunate in that a lot of the architectures are fundamentally simpler. And so when you think about a reconstruction-based method using an autoencoder, the architecture is relatively straightforward. You start with an input image. You've got some layers where you start to generate the feature map. The layers get smaller in height and width. The depth gets greater, and then you get down to this bottleneck layer so that you can actually filter the number of features. And then the model expands from that back up to, let's say, pixel space. The point is that's a very simple architecture that's easy to implement. So maybe you may not need the API that you need for object detection. Other examples for the embeddings-based similarity, a lot of times the workhorse there is pre-trained classifier models. So in that case, again, you've got a pretty good head start in what's available. One thing I think that's worth mentioning, and I've got this described in the presentation in the lower image, is that MVTech has done a good job of, and took the lead on, developing a set of images that can be used for factory-like applications where you have quote-unquote typical parts you might need with defects, or at least you can use those to represent classes of problems that you may want to solve, or we may want to solve for our customers. And so the fact that they have taken this, they created this data set, made it available and open, has enabled other researchers to then use that same data set to benchmark results. And that's, again, just really accelerated the adoption, let's say the innovation and the adoption specific for factory applications. And so the last thing I want to mention is, especially for anomaly detection, because I would say the APIs are less mature, is and this is really something that's part of this mega trend we're seeing in AI, is that open source is becoming very mature. Tools to work with open source. GitHub, for example, has become very user-friendly and ubiquitous for finding, exploring new models that have already been developed. Different authors and researchers have implemented some of these state-of-the-art models and put their source code on GitHub. Websites like Papers with Code link to GitHub, so that you have a system, a support system, if you will, to identify state-of-the-art research that could work for your application, and then you have the software to start with when you solve one of these applications. So now, if we turn our attention to getting this model to the factory floor, this is one of the areas where LMI has focused. And what I'm showing here is a description of the inspection gadget software platform that LMI uses to solve applications for our customers. And so if you look at the center row, what we're calling inspection service, there are just the three components of a typical AI-based inspection. First things first, you have to communicate to a sensor, whether it's an area scan sensor or a 3D sensor. We support either. Then you need to take that image, you need to do any sort of image pre-processing, and then run that through a optimized AI model pipeline. That pipeline might have multiple stages of deep learning based models, for example, for foreground background detection. There might be some areas where you want to zoom in, apply an object detector. There might even be, in a sequential way, an opportunity to apply an anomaly detector. And I'm actually going to show that in an example later. So once you get the model running at peak performance, you need to be able to take those results and then make them actionable on the factory floor. And that's where what we call the automation function of the inspection service. And that takes the results, performs some post-processing, if any, and then we support interfaces to PLCs and other downstream equipment so that the decision can become actionable. So that's I would say the core piece of the inspection gadget. But also what's unique about AI-based solutions, they're all data-based. And so that means we have to take care of a couple things. And one is to be able to archive and support the data that we're seeing, that we're observing in terms of the inspection, so that if something does go wrong, and our customers many times don't have the expertise to service these systems themselves, we can actually work with our partners, our customer partners, and remedy any of the issues that we see. And that could be by way of logging into these systems remotely, looking at some of the data. If there was some known issues, let's say we're finding high numbers of defects, customers concerned, it might be that something in one of the ambient conditions in the factory floor has changed, and we need to update the model with this new corner case. And so we need things like cloud connectivity so that we can quickly and easily support that use case. Certainly this is we're trying to build all of our user interfaces into browser-based environment, so that the HMIs are familiar to our end users and accessible from any device on the factory floor. And then, of course, core services, we have to manage all of the large, huge, really, amount of data that we have coming on and off these devices. So we've paid a lot of attention to making sure that we're not making any mistakes with let's say data swamping hard drives, and just making sure that the system is lean and mean and is robust. So this is the AI inspection gadget, and again, part of all the actual inspections that we deploy. So I mentioned model optimization, and really this is in the context of having to run one of these models on a very compact hardware platform. And One of the things that's very different for AI-based models versus rule-based models is the need for a high-performance processing system. Usually, it's typically a GPU, and companies like NVIDIA have done a great job in being able to take a model that we design or that somebody else designs and run it through their, how would you say, optimization process to generate a what's called a TensorRT model, for example, that just optimizes the model. It might be a transition from floating point to fixed point. It might reference libraries that have been optimized for certain functions. But at the end of the day, you end up with a model of, let's say, known quality, because you can test them, that runs in many cases orders of magnitude faster than if you deployed the development model on that hardware. So that means that we can take some of these complex model pipelines, we can run them through this process, and we can actually deploy them on reasonably priced high performance hardware. In this case, at LMI, we've got a variant of the NVIDIA Jetson Xavier NX that is built into our GoMax NX platform. And so we pay attention to that using optimization tools like this so that we can deploy these models for our customer again on that platform. So here's an example where we actually solved a customer application. In this case, this is food and beverage packaging. And what we're looking for is some of these defects. We call it contamination, or there could be flashing issues. And in this case, we applied both types of object detector, both types of defect detection, both object detection to find known defects, but also there were some defects that we didn't know we were going to have. So we trained a autoencoder, so that would be a reconstruction-based anomaly detector, and we actually combined those into the same pipeline. And so I've got some of the design variables here. We used a faster RCNN for the object detection, ResNet 101 backbone. We set some of the maximum values for detections to improve performance. And in this case, we only needed 80 images to train this model and get greater than 99% precision and recall. So the anomaly detection side, again, I mentioned it was an autoencoder based. In this case, we use structural similarity in the loss function. I briefly mentioned the types of architectures that work here. In this case, you see the depth, the expansion of the depth at each layer, which is pretty typical. We limited the latent space to 256 features, and then imagine flipping that 1632, 64, 128 by 180 degrees, and that's how we get back to the full resolution image for the comparison. And in this case, we used 100 good parts for training. And so here's an example. We did do there was some scaling involved. So I mentioned the image preprocessing. I mentioned object detection to find specific defects. And you can see, if you look through these images, the red squares that show the object detection working. Again, we're looking for the bounding box. But you also see the error intensity map on some of those straws that were grossly misshapen. And so that is the effect of the autoencoder. And what we've done here is we've superimposed the results of both the autoencoder-based anomaly detection and in this case, faster RCNN object detection to give you a view of what the customer would see in production for this application. And in this case, both pipelines or both models run in a single pipeline and under 100 milliseconds on a relatively, I would say, routine laptop GPU. So this is really the overview of what LMI provides for our customers. And basically, we try to provide a turnkey solution to customers who may not have the expertise, but certainly have the need for AI-based inspection in their factories. And it starts with the modeling services, in which case we come to the customer, we talk to them about their needs. Many times, if there's already a vision sensor there, we can reuse existing data. Other times, we'll set up, gather new data, take that data, we'll pre-process it, we'll develop the model pipeline, test it, and then be able to deliver a report and a functional model at the end of developing that. And that's, again, using some of these platforms that are available both to ourselves as well as our customers. And so that would be the first step. And once we have that model pipeline developed, the next thing that we provide is that runtime environment, that robust, high-performance runtime environment that will run many times on the GoMax NX platform. If in fact we need more horsepower, we can redeploy, or we can deploy our system on a server that has more GPU or memory or processing horsepower, if you will. And that's we've got that on the indicated by the inspection device. And then again, that's really taking that model pipeline and deploying it for our customers' needs. And then the last piece that I mentioned was the need for some sort of remote support, so that, again, if these systems start to do something unexpected, it's not as simple as opening up a reference golden part and then doing a comparison. These are all data-based inspections, data-based applications, and so you need a way to gather and aggregate data so that if something does happen, you've got everything you need to make the corrections to get the model or the inspection running properly. And so that's the cloud services piece. And so we provide all of these services and products to our customers. I've also indicated here the automation systems that are obviously part of a total inspection, and the vision systems. LMI certainly makes some of the best 3D cameras in the world, but we also interface with area scan cameras for applications that require 2D vision sensors. And so that wraps up my talk. Here is my contact information. If you have any questions or want to explore any applications, please reach out. With that, I will end my talk and hope to hear from you soon. Thank you.